Scooter. Dr. Durrell, you have the floor.
Okay. All right. Can everybody see my slide?
I can see it.
Looks good.
Yep.
All right. Yay. Well, first of all, I want to thank you all for inviting me. It's a pleasure to chat. It's been a weird couple of years, so it's good to chat about some happenings in science. And this is a talk I give. I particularly like this one because it does, I get to update it with stuff that I work on, because the Virgo cluster is not only a fascinating object, but also it's sort of one of the backgrounds, kind of one of my playgrounds for the research that I do. So it's certainly fun from that point of view. So now, of course, with any of the seasoned observers here, of course, the Virgo cluster is a favorite target for people with telescopes of all sizes. And I'll sort of be talking about it in general and then focus in on a few specific objects that are greatly of interest to me. So, but I do this as the background of using the idea of a city of galaxies, or a town, or a small group of galaxies, because of the different environments that we have galaxies in. So this is just a broad overview of some of the things I'm going to talk about. A little bit about the cluster itself. Basically 3 different research projects that I've been part of over the last 12.5 years on the Virgo cluster, using telescopes on the ground, specifically the Canada-France-Hawaii telescope, which is right behind me here. My background is the CFHT on Mauna Kea in Hawaii. But also Hubble Space Telescope. I use Hubble Telescope for many aspects of the research that I do. And it's always kind of fun to talk about some of that as well. And if time, I'll talk about a little bit of more recent work that I've been doing. So again, I hope everybody hears me all right. And let us begin. Now, I actually study both galaxies and star clusters, specifically globular star clusters, but I'll get to those in a little bit. But just some beautiful images of galaxies. One of the great things that we want to do in astronomy and astrophysics is understand how these beautiful galaxies formed and evolved. And we have lots and lots of bits and pieces, but there's still, we're still trying to piece everything together when it comes to understanding how we get galaxies, like beautiful M83 or the tadpole, elliptical galaxies like M87, which is going to figure prominently in today's talk, the whirlpool, and 3 of these are objects that many people take images of themselves to great success. But what I'm even focusing on is the fact that galaxies live in a variety of environments. Okay, galaxies are not distributed throughout the universe in sort of random scattershot type distribution. The vast majority of galaxies are in groups or clusters. Okay, so and again, this is the idea of talking about towns versus cities. This picture, for example, this background, this is an example of a galaxy cluster where you can have, thousands to over 10,000 galaxies individually, in a part of space, all being held together by gravity. And that includes dark matter holding it all together. And in this picture, all of the bigger galaxies you see are big elliptical galaxies, and these are galaxies that are actually bigger than the Milky Way. If I were to posit a guess, how in this galaxy cluster, how big would the Milky Way be? And I would say it's probably about the size of this thing over here, over on the right. So galaxies come in a variety of sizes, of shapes, and trying to understand, where we get all these different kinds of galaxies is tricky. And as we use digital imagers and go deeper and, in studies, we actually discover more types of galaxies. So it's not just the standard, here's a spiral, here's an elliptical, there's all sorts of stuff in between that we're still trying to understand where they fall in the pantheon of galaxies. So galaxies tend to be in either smaller groups or larger clusters. Well, turns out people do the same thing, okay? This may not be the most popular image for people in this group, but the city lights throughout the United States. But it is an effective way to show where a lot of the population is. And you can sort of see the bright areas, which are the big population centers. Okay, these are the larger cities, okay, interspersed, throughout the United States. But even there, they're not randomly distributed. You'll notice, for example, on the Eastern Seaboard, cities themselves tend to cluster near other cities. Okay, and that'll be another factor of things coming up. But in between, okay, where do a lot of people live are in the smaller towns, either the small cities or the larger towns and villages throughout the United States. And many galaxies, a large fraction of galaxies are in smaller groups, smaller towns, okay? And we're interested in studying both kinds of environments because, not only is the number of galaxies different, but what happens to galaxies in these environments, can differ as well, okay? And of course, if we zoom in on this area, of course, some of you are based here, okay? Meanwhile, I'm down over here, okay, in a smaller area. And the idea of Virgo is it's the nearest big city of galaxies. So as such, it is an extremely important laboratory for us to study how do galaxies form and evolve in the denser environment of a galaxy cluster, okay? So being the closest one, it means it's the one we study the most. There are lots of other good clusters, okay? But Virgo's the nearest one. So for people like me, that's kind of good because I like nearby stuff. I know a lot of people with James Webb having been launched talking about, very distant, very high redshift galaxies. I like my galaxies close enough so I can see the stars in them. So now, before we talk about Virgo, of course, it's good to talk about where we live in all of this. This is one of the better images I've found lately on the local group. This is where we live. Okay, the Milky Way is part of a small town or group of galaxies. Unfortunately, the local group is its name. We couldn't come up with anything snazzier than that, apparently. So this is the environment we live in. So our neighborhood is a collection of about 100 galaxies, of which there are really only 2 big galaxies, 1 medium-sized galaxy, and all the rest are little galaxies, okay? And again, this is pseudo 3D type map here, but this is us. This is our Milky Way galaxy, above average sized barred spiral galaxy, okay? So this is, of course, where we live. And the other big galaxy in the local group is good old M31, the Andromeda Galaxy. And not too far from Andromeda is the Triangulum Galaxy M33. Not as big a spiral as the other two, but I always liked M33. I always thought it was a beautiful galaxy myself. But interspersed, where are most of the galaxies? Well, most of them are these little tiny dwarf galaxies. Okay, the names might be too small for people, but the main thing is our local group, even the local group isn't uniformly filled with galaxies. Basically, it's lots of dinky little galaxies, a bunch of them around the Milky Way, and then you go over to M31 and there's a bunch of them around Andromeda, and there are a few others that are kind of off on their own, IC 1613, and things like that. But most of them are sort of here. So one of the things we want to understand is, well, what happens in this environment? Now, when I was growing up, the local group, people thought, well, it was maybe a dozen or two galaxies. But lately, with big telescopes and extremely sensitive digital detectors, people have been discovering all sorts of extremely faint galaxies, galaxies that actually have fewer stars than some star clusters. And that's one of the new areas of research. We still don't have a complete census of the local group. And that's why I said over 100, I think now, whereas, if, even 10, 20 years ago, people were thinking, it's probably 40 or 50. So it is an interesting environment, but it's only 100 galaxies, okay? However, if we zoom out, okay, to this is sort of the distribution of galaxies. Again, it's very clumpy, but most things are in little groups. And again, there's all sorts of groups here. The Sculptor group, which is, the direction of the constellation of Sculptor, is one of the nearby ones. M81 group is another nearby one. So for those of you who've, seen or imaged M81 and M82, but the nearest big, so here we are, the local group. The Virgo cluster is the nearest cluster of galaxies. Okay, there are other clusters. Fornax is a little bit further, but as far as a big city of galaxies where you have a few thousand galaxies instead of 100, well, Virgo is the nearest one. On average, about 55 or 60 million light years away. Okay, so for astronomy, obviously that's nearby, but so that gives us a place to study. Now, of course, being the nearest cluster, it also has a lot of Messier objects. Okay, Charles Messier himself, noted, 240 years ago that, of the object in his catalog, and at the time he did this, there were only about 91 or 92 in his catalog. He noticed that 16 of them were in this little area of sky, basically in the northern part of the constellation of Virgo and a little bit in the constellation of Coma Berenices. Okay, so that's a large fraction of objects in a small area of sky. But it wasn't until the past century that people began to really appreciate that these objects, this clump of brighter fuzzy objects, was a physical entity. A bunch of objects that people thought were at the same distance. And it was Edwin Hubble himself who was the first person to actually coin the term, the Virgo Cluster. This is a beautiful shot, and this person, I don't want to butcher his name, but is taking lots of other great images. But I just love this image of the downtown area of the Virgo cluster, because the Virgo cluster is nearby, but it's also fairly big, so it takes up a huge amount of real estate on the sky. So this is the downtown core. Okay, so the big fuzzy objects are sort of the Messier galaxies, the brighter ones. But the ones of note here, of course, this is Markarian's chain. Okay, again, very popular telescopic object for those with darker skies. Okay, bunch of galaxies. But the center of the Virgo cluster is actually down here. This is M87, which is one of that is the largest, most massive galaxy in the local universe. So it's not a surprise. It's sort of the middle galaxy. Okay. Now you can only see in this picture all the bigger galaxies. Unfortunately, I don't have it to zoom in here, but this area, just this area alone, there are many hundreds of little dwarf galaxies that you can't see in this picture. You're just seeing the big ones. Okay, so the downtown core, M87, and then these galaxies, they're all somewhat at the same distance, but the chain here might be misleading. They're not all physically connected or anything. It's just some chance superposition. But lots of beautiful galaxies here, and M84 and M86 are two other big ellipticals. Now, when we start talking about, the kind of work that's being done in the Virgo cluster, we want to study, of course, everything that's going on in the Virgo cluster. Now, while, the 16 Messier objects that are part of the Virgo cluster, there's really over 2,000 catalog galaxies in the Virgo cluster. This plot here, this is just a plot of position on the sky and showing some of the brighter objects. So there's M87 at the middle. But Virgo is what we call an irregular cluster. It's not a nice roundish distribution of galaxies all moving around one another. It's actually a bunch of smaller clusters that are sort of getting together to make one bigger one. And the A, B, C here are sort of the name of the subclusters. So sometimes you'll hear people refer to the Virgo A subcluster, Virgo B, and Virgo C, okay? And the bright galaxy at the center of those, M49 is the center of Virgo B, okay? Another bright elliptical. M87 is the center of A, is the big one, okay? But in this diagram, all the little dots are cataloged galaxies that we knew about 10 years ago, okay? So interspersed amongst the big M galaxies, any little dot you see is a catalog member of the Virgo cluster. So lots and lots of galaxies, okay? Some people say, that's a lot of galaxies. And I go, that's job security. Okay. So lots to study. And this is just the middle part of the Virgo cluster, okay? 1, 2, 3, 4, 5, 6, 7 Messier objects just in this area alone, okay? But again, what I study are not necessarily all the really bright ones, okay? As you're going to see. However, the big galaxy, I call it one of these big kahuna galaxies. It's the giant elliptical galaxy M87, about 10 times more massive than the Milky Way. Okay, and this is a beautiful example of an elliptical galaxy. This is a beautiful image taken with the Canada-France-Hawaii telescope. And again, it doesn't have the fancy spiral arms, but this type of galaxy, people have studied this galaxy for a very long time. And I think most people here have probably seen the black hole image from a couple of years ago from the Event Horizon telescope. This is the galaxy. M87 is the home to one of the most massive, supermassive black holes. And that's the one that we actually have the image of the shadow of from the Event Horizon telescope. So it's a big, big galaxy with a big, big black hole in it. And of course, with images like this is just a star in our own galaxy that's in the way. Hard to get it to move, so we sort of have to live with it. Now, what I'm going to show you is just one of the few actual animations I'm going to show. This is an animation actually done by colleagues of mine, Case Western, over in Cleveland. And this is just a quick little simulation of the fact that galaxies move in a cluster. They're not just clumped, they're actually moving. Now, of course, galaxies, it takes a long time for galaxies to move by one another, but if you've got a lot of galaxies in a smallish area of space, they're going to run into one another. They're going to interact. And I'll just show this. Again, this is purely a computer simulation, but it shows you that over billions of years, these galaxies, big and small, will interact. Okay. And what you see with these simulations is that in the middle, you often form a rather large galaxy. And in Virgo's case, it's M87. Okay. But another thing, and this is something you won't necessarily hear as much about, is, a lot of the galaxies stay intact, but you'll notice a sort of kind of very faint grayish fuzz around here. When galaxies interact, some stars actually get thrown out of the galaxies, okay? And this is a newer area of research. This is one that I'm involved with as well, is that as galaxies, get together, the outer stars of some of these galaxies can actually be taken out of the galaxy, and they're actually free floating throughout the cluster. So they're not part of any galaxy anymore. We call these intergalactic stars. And research over the past couple of decades, including some of the work that I've done, it's about 10 or 20% of the stars of all the galaxies are not connected to a galaxy anymore. They're out here in intercluster space. Okay, so that's another interesting avenue that we like to talk about with these clusters. Okay, so imagine stars where there's not many other stars nearby. It's not like being here in the Milky Way. So evolution of clusters is very important. Now, this is an image of the downtown core of Virgo. This is taken with the Case Western's Durrell-Schmidt telescope, which is very good at wide angle, okay, which you need for Virgo. And this is work led by Dr. Chris Mihos, who's another expert on Virgo for sure. So there's Markarian's chain and M87. The big, well, I don't want to call them black holes. I don't want to give you the wrong idea. These are bright stars that have been masked out in the image so that they're not interfering with the analysis. And just for scale, I've added the Milky Way up here. So you get an idea of how big would the Milky Way be on the scale of this image. So you can see these big elliptical galaxies, M87, M86, and M84 are all bigger than the Milky Way. But so again, this is the kind of image many people may, if you've seen pictures of the Virgo cluster, will see. But the idea of this data was to not look at the bright galaxies, but to look at the space between the galaxies. So let's do that. This is a now classic image. It's now 16, 17 years old, that shows that in between the galaxies, you can still see some, light here. Again, that's these stars that get ripped out of galaxies, okay? So Virgo is not just the big galaxies, and it's not just the little dwarf galaxies. It's also some of these stars that have sort of left the galaxies and now sort of permeate the space in between the galaxies, okay? And you can actually see it in this picture, okay? All the light here. These aren't specific galaxies here. There are some you can see the blobs, you can see the galaxies, but you can see the light in here, okay? So this is something that was seen 70 years ago by Fritz Zwicky, and people have been studying it, much more so the last couple of decades. So now that's sort of the broad overview of the Virgo cluster. But what I'm going to start off with is a large project that I've been part of over the last 13 years now. And that is using a ground-based telescope to image the entire Virgo cluster, okay? So this is a nice aerial view of Mauna Kea on the Big Island of Hawaii, one of the truly great observatories. I'm used to being up here. I haven't been there for a few years, but I've probably been on Mauna Kea's summit maybe 12.5 times, taking data throughout my career. And the telescope of note is this one here. It was the first large telescope on the mountain. This is the Canada-France-Hawaii telescope, or CFHT. I am originally from Canada. Again, I got my PhD at McMaster University. So we have time on that telescope, and I've used it for many studies, but it's an extremely important telescope for one of the projects that I'm going to describe. And that is, it's called the Next Generation Virgo Cluster Survey, or simply the Ngvs. Okay. Some of you might go, well, where's the C? Well, let's just say we dropped it for budget reasons or something. People will like that. What this project was, this is something that was started back in 2009. And the idea was to take deep digital images of the entire Virgo cluster, which is not as easy as it sounds, okay? Because you need really wide angle cameras to be able to do that, okay? So here's, one caricature of Virgo. Here's the constellation of Virgo. Here's the constellation outlines. This whole area is the Virgo cluster up here. Now, the last time somebody did this was done with photographic plates in the early 1980s, where people took photographic plates of this entire area to look for as many new galaxies as possible. What we did with this project was to take digital deep CCD images of the whole cluster. So in other words, Virgo in the digital age. And as we zoom in, okay, there's the locations of some of the big galaxies. But this is the, this sort of double circle, this is the Ngvs survey area. How big is this? It's about 108 square degrees. Okay, so, you know, even at the distance of Virgo, you know, to look up at the sky, even if you put your outstretched hand in front of you, it still wouldn't cover the whole cluster on the sky. So some people just studied the inner areas, the core areas. But if you want to cover even out to the, well, not even quite the edges of the cluster, you have to survey 100 square degrees. And with digital detectors and large telescopes, it's actually very difficult to do. So you need a wide angle camera along with a big telescope. We need the big telescope to collect light from very faint objects, but we also need a wide angle camera. Otherwise, it would take forever to take images of the whole thing. Okay, those of you who do CCD imaging can readily appreciate what would be needed to do this. So this is the survey area as it was planned for the Ngvs. Okay, each one of these blocks is one field of the megacam imager at the CFHT. Okay, megacam is a large 1 degree imager at the CFHT. So again, combining lots of pixels with a big enough telescope to truly study the entire cluster digitally. Now, this is just a quick mosaic of all the data. The data were taken over 5 years, from 2009, 2014. And this just shows that area. And you can see all the galaxies. M87 is right here. Okay. Barkarian's chain is here. So, you know, that's just the core area. So we have digital images in 4 filters over this entire area. Takes up a lot of disk space, a lot of analysis. We're still publishing papers from this data, even though the data stopped coming in 8 years ago. Okay, so lots and lots of images. Megacam itself is a rather big mosaic camera. This is the focal plane. Okay, so for the CCD aficionados in the audience, okay, this is it's still on the telescope. It's one of the earliest examples of a mosaic. Each one of these rectangular pieces is a 2K by 4K digital chip, and the whole mosaic together is 340 megapixels. Okay, so you take one image, even if it's a 5-second standard star image, takes up a lot of disk space. Okay, so a lot of data involved in this project. And it covers about 1 square degree, or about 4 times the size of the full moon. So here's the Ngvs area, and here's the full moon for scale. Again, to illustrate how big the full cluster of Virgo is up in the nighttime sky. Okay. You can't do this with the Hubble Telescope, for example. You could never get away with that. This is one of the nice promo pictures. One of the people on the project, Jean-Charles Kiandra, is a fantastic astrophotographer in his own right, and he's often responsible for some of the most beautiful color images taken with the CFHT. If anybody here is familiar with Hawaiian starlight, they do lots of images from CFHT, and he's one of them. Well, this is the Ngvs footprint up in the night sky in the constellation of Virgo, and Ngvs is down here with our friend, the Canada-France-Hawaii telescope. And I love this shot because I like to show this one to my classes, because it's like, okay, you know, why is this a good place to put a telescope? Well, where are the clouds? Down here, 9,000 feet. Mauna Kea is almost 14,000 feet. So a medium-sized telescope with a very big camera is what you need to cover the Virgo cluster. Now, the importance of going digital Okay, this is a key thing. Is again, those of you in the audience who have done lots of your own CCD imaging are very familiar with this. The digital age really helped redefine astronomy. Okay, the original Virgo Cluster catalog from 1985 was on photographic plates, which are not terribly effective. And just to show you how going digital helps, this is an image of one of the faintest galaxies that were seen in that survey. I mean, you could be mistaken if you look at this and go, is that really something, or someone just put a thumbprint on the image? This would be what's called a round dwarf elliptical galaxy. Well, here's the same galaxy, same field area with the Ngvs. Okay. The telescope's a little bit bigger, but most of it is because of digital technology. So what looked like a very faint little smudge that you won't get much out of, we actually see it as a very bright galaxy. And this is a dwarf galaxy. This is 1% the luminosity of the Milky Way. So not a very big galaxy, but looks impressive once you go digital. So now, of course, we can get beautiful images. So, just thought I'd do a smattering of images from the Ngvs data, including, again, Markarian's chain. Okay. And again, you're only going to see the big galaxies here, but just some nice images from certain things, some of the galaxies. And again, this is all digital data. So there's over 100 people, over 70 people on the Ngvs, and they all have different interests. Okay, some people want to study the big galaxies. Some want to look for the dwarf galaxies. Some want to study the star clusters. That's where I come in. Okay, so it's a kind of a survey to do as much as you can with the data we have, but just showing you some of the bigger galaxies and their phone numbers here. Edge-on galaxies, S0s. I like looking at these pictures myself. A nice barred spiral. So those are some of the brighter galaxies. But if you look carefully at the images, you'll also see, like here, some of the faint dwarf galaxies that are in amongst all the bright, bigger ones. Another one up there. Because that's one of the things, with the data going digital, some of these images go much deeper than have been done, ever. So the idea is that one of the goals of the project was to find new galaxies, okay? Get a more complete catalog of the Virgo cluster. Okay. And in the core region, we've done that. We've actually done it for the whole cluster, but we've only had time to publish the middle. Now, this is probably a rather busy plot. So what are we looking at? This is the 4 square degrees of the inner part downtown Virgo. So M87 at the center, M86 just off on one corner. So this is where the densest, this is where the most galaxies are located. Because you won't be able to see them at this stretch, the red and the green circles denote galaxies that were known before the Ngvs. Okay, so, and roughly to size. So, a lot of these, the red ones were originally from the Virgo cluster, the photographic survey. Okay, but because of the depth of the data, things in blue are new galaxies that were discovered with this data set. Okay, in this image alone, 154 new galaxies come out. Now, most of these are dim little dwarf galaxies that 20 years ago you wouldn't have been able to see with the technology at the time. Now we can. So lots of these little dwarf galaxies out there. And it's kind of cool. Okay. And here's some zoom ins. Now the colors were changed for these little insets. These are still new galaxies. But these are mostly dwarf galaxies. Galaxies, like I said, maybe 1% the number of stars is the Milky Way. Some even less than that. So these are all new galaxies and they stand out. I mean, some of these you go, that one's, it's not even, you don't even need a fancy computer algorithm to find them. It's just like, how did you find it? I just looked. I've got all these images on my research computer, and I'm just looking at them. Yeah, there's one. Okay, so. Now, a couple other little things that I work on in the Virgo cluster is I study globular clusters. Matter of fact, my original research was studying globular star clusters, both in and around other galaxies. In particular, like I said, even today, I look for globular clusters around other galaxies because these star clusters these are the old ones. These are the 11, 12 billion year old clusters that tell us a lot about the early days of galaxy formation. Okay. Now, the Milky Way has about 160, some say close to 170 of these things out in the halo of the Milky Way. And we've studied a lot of those, for a very, very, very long time. And this is a beautiful Hubble image of one of them, M80. Okay. But most other big galaxies all have them too. Okay. And they actually tell us about other galaxies. Matter of fact, the really big galaxies have even more of them. For example, this is just a black and white. This is just, I think this is the G filter, which is a green filter of M87 from the Ngvs. And you see all these dots here. Well, this close to M87, these dots are not stars and they're not background galaxies. Those are globular clusters surrounding M87. Okay. That's what probably 99% of the dots you see here are these star clusters, but because of the distance of the Virgo cluster, they just look like dots. So they don't look like beautiful vistas of stars like I just showed you. Matter of fact, M87 has 14,000 of these globular clusters around it. Okay, so almost 100 times more than our own Milky Way. It's quite amazing in its own right. So how do you study these things? Well, you have to study things that look like stars, but aren't stars. Confused? This is one of the projects that I led as part of the Ngvs, was to study these things, both in and outside of galaxies. But when you're using data from ground-based telescopes, the images of stars only get so small. So what do we look for? We look for anything on the images that looks like a star. Problem is, so do stars. And here's an example. This is actual data from the Ngvs. Okay, and this is near the Virgo core area, and I picked this one for a reason, because this is a galaxy we discovered about 15 years ago. More on that in a minute. But this is a ground-based image. And you look at this and you go, okay, well, what are we looking at? Well, most of the things on here look like stars. Okay, a couple of fuzzy things. This thing's fuzzy, this one's fuzzy, okay, this one. Okay, the problem is those things are all different things. I've used Hubble Telescope data to factor in. So here's a background galaxy. Okay, that we can get rid of. We can tell that on the data. This is a little dwarf galaxy. Okay, we're interested in that. But these things all over here, these other three circles, these all look like dots. They all look the same. So it takes more digging to figure out that this one is a star in our Milky Way. These are three background galaxies that look like stars. And then one of these is an actual globular cluster. So background contamination is a big factor in these studies. So we have to be very careful how we select. We use different filters to select out which of these things are likely star clusters, which of these are stars, so we can toss them out, which of these are background galaxies that we can toss out. And, we can actually map out, not the red dots, but the contours. We can actually map out where the globular clusters live in the entire Virgo cluster. And as expected, most of them are in the galaxies, but there's lots of them in between. So these are globular clusters that are orbiting between the galaxies. Okay. So one of the many results that are coming from Ngvs. Now, of course, these are all wide view panorama. we can also use the Hubble Telescope to take a closer look. So don't just look at the city. You know, if you fly over a city, you can see at night, you can see the streets, you can see the downtown core where all the city lights are. But sometimes you want to get a closer look, like getting down into the stadium, okay, down at the people level, okay? With that, this is where the Hubble Telescope comes in, okay? Now, the Ngvs is a project that can only be done with a ground-based telescope with a big camera, okay? Because you need field, you need wide angle to do that. But if you want to zoom in on certain parts, this is where Hubble is in its glory. Been part of numerous Hubble projects over the years to study stars and star clusters in nearby galaxies. The project I was part of 15 years ago was, so here's that image of the downtown core again. Okay, by this point, you should be on either well adjusted to it or bored of the middle of the Virgo cluster. Okay, here's M87, here's the other two big ellipticals. Well, we asked for time to image one field in the middle here. Okay, there's no galaxies in this area. What we asked for is we used its deepest camera and we basically sat in this field for dozens of orbits. Okay, that's a lot of time. It's actually one of the deeper images ever taken with Hubble. Not quite as deep as the deep fields, but you know, it's approaching that level of depth to point at a blank area of the Virgo cluster. So you can imagine us trying to sell this to people. What do you want to point at? Nothing. Excuse me? So we want to point in between the galaxies, and we wanted to look for the stars that are between the galaxies. Okay, so we finally got the data, we analyzed it, and this is a color image of the field. Now you won't find this image as one of the press releases because it's not as stunning as some of the ones that you've seen from Hubble. And so this is the color image of the whole field. And most of what you see is not what we were looking for. Okay, most of what you see here are background galaxies. Okay, we're not interested in those. I know colleagues of mine who are interested in those things, but that's not what we were looking for. And I can't even really show you unless I could zoom right in. Okay, but in between, we found individual stars that are red giant stars at the distance of Virgo. You can't see them with ground-based telescopes. With Hubble, you can. Okay, and so here's a close-up of that field, and shows you one of the greatest inventions in astrophysics, which is the circle. And what we were looking for are the little dots that you can see in the middle of the circles. That's what we were looking for. Yeah, these are stars that aren't part of a galaxy anymore. They're out in between. And we found 5,000 of them. Okay. But there's more. Okay. In amongst those stars, there were 4 objects that look like globular clusters. With Hubble, you have just enough resolution that you can maybe see some of the stars. So it looks a little more like a globular cluster. And here are the images of the 4. Okay, this one's the most convincing one. Okay, these are 4 intergalactic or intracluster globular clusters. So orphaned globular clusters. So we found 4 of them in this image. Okay. So again, it's one of those things where we try and get everything we can out of the data. Okay, now, for those of you who've looked at globular clusters, either with your eye or with CCD, okay, these are not going to be the most impressive ones you're ever going to see. Okay, the close-up of IGC1 here, this is the Hubble image. It doesn't look like much, but that's because it's 54 million light years away. This globular cluster in our galaxy is only 33,000. So the difference in distance helps. But another neat thing about this image is we didn't know what all was in this field. And this little object is a new dwarf galaxy we discovered, quite by accident. We didn't know it was there. No images of this area beforehand were deep enough to show this thing. It's not the red thing, but this is a dwarf galaxy. Okay, we call it a dwarf spheroidal galaxy. It's probably, yeah, about 0.1% the many stars as the Milky Way. Okay, so it's just a little dwarf, but, and again, well, how people say, well, how'd you discover it? I said, it wasn't hard. I downloaded the data and said, look, there's a galaxy in it. And how do we know? Because you can actually see the stars if you look closely in the galaxy. And the brightest red giant stars in a galaxy have a known wattage. So we can actually use that to get a distance. And we can show that this thing is indeed at 54 million light years away. So it's in the Virgo cluster. We can actually confirm that. Okay. Now, this is a Hubble image, okay, which zooms right in. And just to sort of, in one of my final slides here, zoom in. These are some of the dwarf galaxies we discovered as part of the Ngvs. Okay. So with ground-based data, you look at these and you're kind of going, is that really a galaxy? Are you sure? Okay. And I'm sure some of you look at these going, really? There's a galaxy there? Okay. But this one hit this one down here. That's our little galaxy. There's a zoom in of it. So with a ground-based telescope, you can see something fuzzy and you're going, wow, that doesn't look like much. And then the Hubble image, that's what it looks like to the Hubble Telescope. Okay. And 40 orbits. So, you know, we can look at Virgo wide angle or we can zoom in, but we can learn all sorts of wonderful things about the cluster. And the final thing I'll mention is, you know, we're also studying galaxies that are not the norm. Okay, we think of a big elliptical and spiral galaxies. Well, the last few years, people have, because of the big telescopes now and digital detectors, people have started to discover an interesting, it's not a new class of galaxy, but we've started finding these galaxies that are very, very dim, very low luminosity, very low surface brightness, but are larger than typical dwarf galaxies. Now, they've been given a name. They're called ultra diffuse galaxies. They're not really a new class of galaxy, but we're now finding them more often with digital data. And that's some of these galaxies. These are the actual images from a project that I was part of, again, using data from the Case Western Telescope. Okay, so these would be, if a dwarf galaxy is, say, the size of my fist, like the little one we showed, then these galaxies are probably, you know, many times bigger. Okay, but they're still very, very, very low surface brightness. So, I mean, you won't find these with a small telescope. Okay, they're just much too low surface brightness. So you need big glass and digital detectors just to see them. So we found one of these and we said, well, let's get some Hubble data on one of them. So this is just new stuff. We just published this. Okay. This is a Hubble image. This is the ACS, the Advanced Camera for Surveys. And up here, this sort of fuzzy thing is a galaxy with the, well, dull name of VCC 615, Virgo Cluster Catalog. Now, this object is 20,000 light years across. The Milky Way is 100,000. Okay. Typical dwarf galaxies are a few thousand light years across. But you'll see, you can barely tell it's there, even with the Hubble telescope. So, you know, with these big telescopes, we can start seeing, you know, this sort of, kind of, they're like dwarf galaxies with a bit of an edge, with a bit of a size thing to them. So we're starting to learn more about these. And again, we can see the red giant stars in this galaxy, and we also showed that it too is in the Virgo cluster. So, you know, depending on what you want to do, there's all sorts of things in the Virgo cluster, and I wanted to highlight the cluster itself, but also some of the things that we're looking for. You know, and for those in the audience who are like, I wish you'd shown more spiral galaxies. Sorry about that. So basically, that's sort of at least one view of different parts of the Virgo cluster. So I will end by saying thank you for everyone. Thank you for the invite. And I leave with this picture of some of us on the Ngvs. This is me right here, underneath the Canada, France, Hawaii telescope. You know, as we had a meeting in Hawaii for some of the initial analyses of this big, big, big project. So I will end it there and see if there are any questions. I don't know.
Great. Thank you very much, Dr. Durrell. If you would like to ask a question, you can unmute yourself and ask, or you could also type it into the chat, and I think Bob would not mind reading that to us.
Certainly. First chat question is NGC 2419 a near example of a globular no longer associated with a particular galaxy, ripped away through a past interaction, or is it gravitationally bound to the Milky Way, just orbiting much further out than the, hold on, I got to scroll.
Wow, what a, okay. Whoever wrote this question is, this is one of the slides I actually had to take out, which actually showed NGC 2419.
Yeah. Anyway, let me finish.
2419 is an interesting globular because it's one of the more distant globular clusters. It used to be called Intergalactic Cluster because at the time people didn't have a good idea of how far out globular clusters extended. It is a member of the Milky Way. However, it's a fairly big cluster. It's just not near us, so it doesn't look that impressive. So it's not intergalactic. But I believe 2419 is one of the globular clusters that was brought here as part of another galaxy. One of the new things in globular cluster research is we're starting to be able to tag globular clusters as these ones probably formed with the Milky Way early on, but there is a fraction of globular clusters that actually were part of dwarf galaxies that came in, got absorbed, eaten, digested, however you like, by the Milky Way, leaving its globular clusters, intact. So yeah, 2419 is an interesting history. 60 years ago, they called it an intergalactic wanderer. That was its name. It is a distant member of the Milky Way halo, though, so it's not true intercluster. But that's a wow. Talk about jumping right in with a awesome question. Yeah, I used to have a slide showing NGC 2419 for that reason. So you got me.
That was from Wayne Faneuf. I didn't give his name. Sorry, Wayne. I don't. Oh, thank you for coming. That's from Mark. To everyone. I have a question.
Sure.
Regarding what's the methodology for counting the number of stars in a galaxy of any type?
Oh, counting stars and galaxies. That's a very difficult proposition. I mean, to try to give you the best version of how to do it, and it's still only an estimate, is we can measure the total luminosity of a galaxy. Okay, that's fairly easy. Okay, if we see all the light, we can measure it, we can calibrate it. So we know, for example, this galaxy has so many million times the luminosity of the sun. But to get to the number of stars, you then have to sort of go, well, what's the average luminosity of a star? And that is a trickier question than you think it might be, because you have to have a full understanding of how many bright stars, medium stars, and the huge amount of really dim stars that you can never see. So that's a rather big correction factor. So that's why when it comes to numbers of stars, it's still pretty uncertain. Even if you ask people the Milky Way, if you say, how many stars are in the Milky Way? We have a good idea of its total luminosity, okay, in solar luminosities, how many suns of light. But the average luminosity of a star has a wide uncertainty. So you're still going to hear, I hear 100 billion, 200 billion, 300 billion stars in the Milky Way. And it almost sounds like, well, astronomers really don't have an idea. I don't want to give that impression, but it's a difficult thing to go, because like even that little dwarf galaxy I showed you with Hubble, we can only see the top 1,000 stars. And then we have to make assumptions for every bright star that you do see, how many below that can you not see? And that takes a bit of modeling, and there's a lot of uncertainties there. So it's not exact. You can get in the right ballpark. But yeah, even for the Milky Way, we don't know to high precision.
Yeah. All right, we have a question from John Panuto. Can you talk a little about the globular clusters, how globular clusters form? Are they amalgamations of stars that did not become galaxies? Help.
Yeah. First of all, if I knew precisely how globular clusters form, you probably have heard of me before today's talk. It's still an open thing, but the idea is that no, they're not amalgamations of stars that never became part of a galaxy. Globular clusters formed in the earliest stages before many stars in the galaxy formed. So as a galaxy, let's say you've got a blob of gas and that will eventually become stars in a galaxy. The globular clusters were these dense knots of stars that formed in very small but very dense high mass regions. Like I'm trying to think of a good analogy, just like, you know, like clumps of something. Think of a gas cloud, but there's these dense little knots, because you need special conditions to make a globular cluster, because a globular cluster, an average globular cluster is, 100,000 to 500,000 stars in a sphere smaller than 100 light years across. So they're very dense clusters of stars. So many of them formed at about the same time or slightly earlier than galaxy stars. Dwarf galaxies have them. That was my PhD thesis a long time ago. Even little dwarf galaxies, not the littlest ones, but little dwarf galaxies have 3 or 4 of these. So they are not stars that did not become galaxies. They're a part of the galaxy formation process. Stars themselves can form in, collapsing clouds of gas, like our sun did. But to make a globular cluster, you need a kind of denser, thicker cloud of gas to make those. And we don't have those conditions today. This is why all globular clusters are old, okay? There are some young ones out there, not in our galaxy, but to make high mass, dense star clusters was easier 11 billion years ago, not so easy today. So that's why you don't see any new globular clusters in the Milky Way. We form lots of stars in the Milky Way. We form small clusters like the Pleiades and the Hyades. But big things like globular clusters, we don't have the conditions to make those. So they're an integral part of galaxy formation, but they're not leftovers or anything. Okay.
All right.
So hopefully that helps. But yeah, it's just to make these are massive clusters that are very dense. So they're not, it's harder to make those than to make the Pleiades or the Hyades, which are fewer stars, lower mass, and can still form today in the Milky Way. We don't have the conditions to make globulars today.
Okay, John Panuto follows up, says, great answer, thank you. Back up to the counting. This is a follow-up to the previous question on determining the number of stars in the galaxy. This is from Wayne Fanoff. Again, Can you do calculations based on mass? And by the way, if you want further clarification, Wayne, you can turn on your microphone and ask it directly rather than type it out.
Yeah, can you do calculations based on mass? Well, very often the mass is usually the more important quantity, but mass you cannot observe directly. The thing about, like, for example, all the images I showed you in my talk, with data like that, we can measure the luminosity of a galaxy quite well. To figure out its mass, we actually have to do other studies. I mean, you could sort of say, well, if the galaxy has this many stars, how much mass does it have? And then that has the same uncertainties like counting the stars earlier. But you can determine the actual mass of galaxies by watching how things orbit. This is where the globular clusters come back in. Nice question, by the way. You're 2 for 2 there, Wayne. You can measure the mass of a galaxy by watching how the globular clusters move. Some dwarf galaxies have a couple dozen globular clusters, and that's enough that you can measure their speeds and actually determine the mass from physics. And we've done that with some galaxies. With big galaxies like Milky Way, that's how we know how much mass is in the Milky Way. One of the ways to do that is we measure the motions of the 160 globular clusters that we do have. And that's what tells us the Milky Way has this much mass and only this many stars. And this is where all the dark matter comes from. So we can determine the mass, but it's actually tricky to do it directly. But mass is probably one of the most important things to learn about a galaxy. Matter of fact, my PhD supervisor, Bill Harris, figured out a decade ago that the number of globular clusters in a galaxy is related to its total mass, including dark matter. And people are still trying to understand this relationship. So if you have 5 globular clusters, that means a mass of this. If you have 10 globular clusters, it means a mass of this. There's some sort of connection between the physical number of globular clusters and the total mass of a galaxy. And people are right now still trying to understand why that is. But that's something that was suggested 20 years ago, and it's only the last 10 years that people have started modeling it, trying to understand it. So that's some, both your questions are dealing with leading edge research, which I don't want to sound like I'm giving you the runaround. It's like, we're still trying to figure it out. As like I said, mass is, you can't just look and see mass. That's the problem. At least luminosity we can see. Okay, so for example, that dwarf galaxy we discovered, I don't know the mass of that galaxy. But by the data, I can calculate how many suns, how many solar luminosities it is. That we know. But we don't have a mass. There's no globular clusters in that thing. So we have no idea what the mass is. Okay, probably won't for a very long time.
Yeah, Wayne has said he doesn't have a microphone, unfortunately, but he did say, got it, cool. So anyone else, I don't see any other questions on there. If anyone else would like to speak up using a microphone, go ahead. We'll try to get them all in.
I got a question.
Sure.
Has anyone ever analyzed M87 and tried to map the distribution of the velocity of the stars? Like, I assume maybe the younger, more metal-rich stars are toward the center, while the older.
Not the velocities of the stars, but the globular clusters, yes. Some of the people on the Ngvs do just that. We actually did a paper a couple years ago where people have been getting radial velocities of globular clusters in M87 for about 30 years now. We probably have velocities now for a few hundred of them. So we actually have a good idea of the mass of M87 because of that. And we actually go out far enough where you can see that there's some globular clusters, their velocities are different enough. They're not part of M87. They're in between the galaxies. Yeah, M87 is the most by number, the biggest globular cluster system nearby. So it's been studied since the mid 80s to very, high precision. Yeah, we learn a lot about it, but getting velocities is hard. I mean, it takes a lot of telescope time to get a velocity for a single cluster. So I don't know what the latest tally is. I know our group got a few hundred, but if I were to take all the catalogs, put them together, maybe 1,000 or 1,500 have velocities. So, you know, people actually say, what's the mass profile? How does the mass fall off with distance? We actually have that for M87. So it's one of the most well-studied galaxies because it has thousands of globular clusters. That helps. It's tough to do this with 5. 14,000.
I was actually asking about the metallicity, you know, the metal content of the distribution of stars in the galaxy.
It can, but one of the things we learned about all the big galaxies is the metal content. It's actually bimodal. There's actually a fraction of globular clusters that are red and fairly metal rich, not quite solar, but maybe half solar. And then there's a bunch of globular clusters that we call the blue ones, which are much lower metal content. They're all about the same age. Okay, even the M87 ones, I mean, the red ones might be 10 billion years and the blue ones might be 12. But there's no young globular clusters in M87. There's a lot of red ones, and sort of, this is oversimplifying it a lot, but the red ones we think formed with the galaxy. When M87 got built up, you know, so long ago, the blue ones may have come in from other galaxies and got added from dwarf galaxies. In other words, M87 brought in a lot of blue globular clusters by eating lots of little galaxies. Because the red and the blue star clusters are not distributed the same. The red ones follow the light of the galaxy and the blue ones kind of keep going. So it's like, so many of them were added later. So, but yeah, I can't remember what the fraction is of M87, but I want to say, I don't remember the fraction, but it's not quite half and half, but yeah, you've got them both. But they're all old, like I said.
Okay,
did that help? That question, there's a lot of avenues in that question, so I took one. But yeah, it's well studied. Most big galaxies have, if you look at the colors of the globular clusters, it's like you got metal rich ones, metal poor ones. I should flip those. You know, bimodal like this, and these ones tell a story, and these ones tell a slightly different story. So, and the other big ellipticals, M49 has the same thing. And we've been trying to understand that for 35 years too.
All right, we have a question from Uriah Kleiss. Go ahead.
Mm-hmm.
Hey, thanks. That was a fantastic presentation. Really enjoyed it. I
liked it.
You were talking about the CF HT and going there 12.5 times. What was the daily life like? When did it start? When did work start? What did you do during the day, and how did it end?
Well, things have changed a lot with observing. When I was a graduate, my first time there was 1992, and back then we still had traditional observing, which means you wrote a proposal, you got time on the telescope, you would fly to Hawaii, you would get the telescope for a certain number of nights, take your data if it was clear, and analyze it. So the first half dozen times I went, I would go, you'd stay, you don't stay up at 14,000 feet. You go up at night to use the telescope. The dorms are at 9,000 feet. So let's say I had a 4-night run. For my thesis, I had a 4-night run, for example. I had 4 nights that were dedicated to my project. I would be at the dorms at 9,000 feet where the air is a little thinner, but not bad. That's where you'd stay during the day. You'd probably read, get caught up on email, play some pool. But you wanted to stay acclimatized, so you didn't go down to sea level. So I was not at the beach during the run. So I'd stay in the dorms, and then right after dinner, you'd drive up the half hour to the summit, take all your calibration data. If it was clear, you observed all night, then you drove halfway down the mountain first thing in the morning, and then you would repeat. Okay, that's classical observing. These days, remote observing has taken over, which means even if I had a project of my own on the telescope, I would write a script and stuff and say, this is where I want you to point. These are the filters. They would put it in a schedule and they'd have seasoned observers take the data and I would download it. So observing with the big telescopes now is somewhat different now than 30 years ago. The last time I actually took data at CFHT, I think was about 15 years ago. Took it myself. So I kind of miss those days. It was easier when I was younger, but I love going up the mountain. Mauna Kea is an incredible place. I'm a telescope geek. I am one of those astronomers I was like 7 years old when I decided, I liked astronomy, and I wanted to be an astronomer since before I went to high school. So I had telescopes. I had early Dobsonians. I played the game. And, so I kind of liked the observing, and going up Mauna Kea was just an amazing experience. And like I said, I do miss the classical observing, but it was also inefficient. If I went down on a run, one time I had 3 half nights, myself and my colleague, and then 2 other people had the other half nights. We were clouded out all 3 nights. The only thing I got out of that entire run was a sunburn on my back from snorkeling. So that wasn't very efficient. The new system, it's Q observing. It's like, here's all the programs, here's the conditions you need, here's the different areas of the sky. And they might take data for 5 different programs on a night if it's clear. And then they'll let you know, oh, Dr. Durrell, some of your data got taken last night. Not all of it, but some of it. Oh, great, wonderful. Let me know when you're done, that kind of thing. So things have changed a bit. And some telescopes like the Keck, you can control them from sea level. You don't even need to go up the summit, even if you had classic observing. So, things, just the last 15 years, things have really changed as far as observing with the big telescopes. Like I said, my last time at CFH taking my own data, like I said, I think was, I want to say 2006 or 2007. Got some good data, but now, with Ngvs, for example, nobody on the team took the data. It was taken by seasoned observers. And then they tell us, oh, by the way, observations for this field got taken. Oh, okay, I'll have a look, and download it. Takes a while because these are big images, and see what's going on. Software pipelines and Q observing now rule the day with large telescopes. So you don't want to have to do all the pre-processing on those mosaics. Okay, so for those of you who do your own flat fielding and dark corrections and stuff like that, you don't want to do those individually anymore at the big telescopes. They have pipelines that do it, and they just say, your data have been flat fielded. Thank you. Because it takes a lot. Megacam is now small compared to some of the other cameras out there. That's 40 different CCDs with 40 different responses and 40 different flat fields. So you have to kind of do those individually, and that becomes computer intensive is the word I would use, but it's messy reducing those things. So like I said, back in the days we used one CCD. It's like, okay, we'll take all these dome flats, we'll take all these flat fields, we'll take the dark exposures. We had a standard way to do it, but with these mosaic CCDs, there's got to be more software. The Vera Rubin Observatory, which should be starting up in a year and a half. That camera is 1-point-something gigapixels. I forget the exact number. There's a data reduction nightmare. Okay.
All right,
Megacam is only 340 megapixels.
Yeah. Are there other questions? You can turn on your microphone and ask.
Sorry, I'm a little long-winded on my answers. I've got a big mouth and I use it.
Oh, no, it's great.
I'm from teaching all these years.
We don't mind.
Okay.
Any other questions?
Okay,
Thank you
that's-
thank you for an informative talk on the Virgo clusters. One of my favorite to image as well, just for fun.
Oh, well, I'm glad you liked it. Like I said, I figured there were a lot of seasoned observers here. So, I made that assumption. Well, it must be. I'm looking at, Doug here. He's got game with his background. I just love that background. That's just, I don't have anything to rival that. I'm like going, oh, geez, I really got up my game.
That was taken. I took that just last October, and that was only with a 4-inch refractor.
That's with a 4-inch refractor?
Yeah.
Oh, geez. Holy smokes. Yeah. Like I said, I never did much my own astrophotography back in the day because it was a little more difficult back then. But yeah, it's I just love these. I just love these images. I love galaxy images.
I did film back in the 70s and the 80s. I know all about it.
Oh my God, oh boy, I've forgotten all the terminology.
Oh yeah, cold cameras, hyper film.
Hyper film, that's it. Yeah. Wow. Yeah, well, that's a fantastic image. I just love it. So, but yeah, it's a great thing. And like I said, some of those images I was showing you were by what you might call amateurs. I think that term has long since been superseded. Some of those